very briefly there. See if I can make this one out right. Oh, that was definitely distinct. And that's at 18 centimeters on here, plus the 2 centimeters from the top, so we got 20 centimeters and we predicted 21.4. It's no vibrating string lab, but, or demonstration, but hopefully it's close enough. Likewise, we can determine the speed of sound doing something similar, figuring out where the harmonic is, and then just from the harmonic, figure out the wavelength, and then from the wavelength, we can find the speed of sound. And there's one version of the lab where you do several of them, and then basically dual plot. The slope is related to the speed of sound. All right, while we're here, let's go ahead and do this, the third harmonic for 400 hertz. Wavelength is still going to be the same, that hasn't changed. But for the third harmonic, or the first overtone, what will the length be? Point 643
125
units.
meter.
It should be 3 times this. Because if we look over here, going to the length of the first harmonic and third harmonic multiplied by 3. All right, so it should be third. And so 64 points to do, so it should be somewhere around here. Let's see how close we get. What was that?
I was going to say you probably need to catch for that one.
We will find out. I'm actually more apt to kick it over than to spill water here, but. I at least want to get it close. This was one of the few labs that when you're doing it, there are these things, these false harmonics as you go down. It sounds like it's getting louder, then it gets quieter, then it gets louder again. So it helps to actually know what you're looking for before you look for it. In general, not a good way of doing science, but for this lab, it's the difference between reasonable results and ludicrous results. That was it right there. There we go. That's the third harmonic. And that's about 59.5 centimeters on here, plus the 2 centimeters, so 61.5 centimeters. And we predicted 64.3 centimeters. So we're about 3% off. No, actually, more like 5% off. All right, questions? All right, time to bring out the pink tube. All right, so we got a harmonic there. That's actually the second harmonic. Third, fourth, fifth, and briefly on the sixth. All right, so that's our next set of predictions. We're going to just take a small little break here, and we'll come back. We'll see how well this works. And you will be amazed and awed at physics. 2 free ends. Physically, it's represented in this tube by the fact that they're both open. There's nothing for it to bounce against. So, what would the first harmonic look like?
Something like one node and two antinodes.
Okay. I know the free end has an antinode, so they have to be at their antinodes at the end, and we got a node in the middle. I'd love to be able to test the node in the middle, but unfortunately, any device I put in here in order to listen to the silence in the middle would disrupt it, and the pattern wouldn't hold. How many wavelengths is that? So that is something like L.
If full one is 2 circles, this is 1 circle.
All right, so going with that, if that's a full one there, basically we're going from antinode to antinode. We're chopping off the 2 quarters at the end, leaving us with a half. All right, so that's a half of a wave. There's, for the wavelength, it's just 2 times whatever that length is. Second harmonic. Or the first overtone. See people poised to draw with their fingers, but
Would it be that one?
I still have to have 2 antinodes. I have an antinode at each end.
Like full circle in the middle and 2 pieces from sides. Yeah.
Yeah. You know, I just basically extend it until I get another antinode. So how many waves is that?
1.
Yeah. It's just 1 wave. Because I added a half, and just like for the other 2 examples, I add a half each time. We'll go through the 4th harmonic. And so add a half each time. And then start to look more like a DNA spiral. So using Marina's terminology, we're adding the circle every time. So here, since we're adding, it's the 3rd harmonic, so it's 3 times what we had up there, so that's 3 halves of a wave. And here, L is the 4 halves, or 2 wavelengths. Illustrating the 2 wavelengths there. The first wave, that, and that's the second wave. So our wavelength is 2/3 of L. And the wavelength is half of L. All right, so let's make our predictions. we're dealing with sound, so speed of sound. We'll stick with our 343 meters per second. That's going to be equal to the frequency times the wavelength. What we're going to do is predict what the frequency is. So we got 343 meters per second is equal to frequency times, well, for the first harmonic, my wavelength is twice the length of the tube. So let's figure out what the length of the tube is. Ah, there's the meter stick. Need to straighten it some, and it comes out to, probably easier if I went from that end, and I don't have to subtract. 84 centimeters. The length is 84 centimeters. Which is 0.84. Meters. All right. So for the first harmonic, that's the one that we can't hear, but show you why I made that claim. What is the wavelength for the first harmonic? .68 meters. Just twice the length of the tube. And so my frequency is 343 divided by 1.68. Units? All right, so 204.16 hertz. So I'm sure all of you know what that sounds like. See if we can nail it. Oh, perfect, you got it. Is that 206? Well, in order to know, hopefully I don't have to turn this thing on again and wait for that. All right. But I do have to wait for it to think about what it's going to do. All right, so 204.1666617. All right, so this is what 204.17 sounds like. And this is the lowest one I can generate. It sounds like a higher frequency to me. A noticeably higher frequency. All right, so what's happening here is as I swing this thing around, this end is whipping through the air, and so the speed of the air increases up here compared to down here. With the speed of the air increases, it drops the pressure here, and so there's more pressure at the bottom, which is not moving as fast than up here. And so that difference in pressure is causing air to come up through the tube. The ribs get to vibrate, and so then we get the harmonics. In order to get the 204, I need to go more slowly. The faster I go, the higher the frequency. So at 204, I can't go slowly enough to create enough pressure differential to get air to go through it. So the second harmonic is the first one that we possibly can hear. So let's make our prediction for the second harmonic and see how close we get. So that's F1. For the second harmonic, speed is the same, our wavelength is different. What is the new wavelength? If I cut the wavelength in half, so it should double the frequency, so it should have been twice that. All right, so first let's figure out what that sounds like. And so 408.33. And that sounds exactly like the sound I just played, if you trust my memory. All right, so sort of have a mental image, impression of that. Now, how close are we? Well, we can do that off of memory, and if you have a really good ear, you might be able to tell how close we are. Now, there will be a difference in sound quality. The timbre is different because this is a plastic tube and that's a speaker. This probably cost $1, and that probably cost $20. Actually, I have no idea how much speakers go for nowadays. So the way that we can check it is to play them at the same time and listen to see if we can hear any beats. There's a slightly different vibrato there that wasn't there before. You hear the trill? All right, so we are at least close enough to hear beats. Let's go ahead and make a prediction for the next one. What is the frequency for the third harmonic? All right. That's 612.5. Play them at the same time. I hear a little bit of an extra trill there, but not if I do it wrong.
Slide out a little further.
Pardon?
That was it, nothing, banjo. That's the sound that the instruments make whenever they're out of tune, so let me get tuned a little better.
Ah. So you were playing with plastic tubes?
What?
You're using plastic tubes?
No. I was using a trumpet.
Metal tubes.
Basically.
Yeah, I heard like a tuba. How far the sound actually travels in a tuba is the size of a telephone pole.
Yeah, it's just all wrapped around it, so.
Yeah.
What was the little one?
Anyway, 2 free ends. And you can be sure on the last test, there's gonna be some question about, 2 fixed ends, 1 fixed, 1 free, and 2 free ends. If you look at the old test, you'll see them. You'll see old versions of it. Questions to hear.
Where did you get that thing?
That was just lying around. I have one, the one that I used to use is one that I found in our backyard, buried underneath the ivy. But this one was, I don't know, my predecessor might have bought it, or a student left it or who knows. I'm amazed at some of the stuff students leave, so could very well be that. All right, so let's talk about Doppler shift, sonic booms, neat junk like that. I'm about to do some incredible, absolutely incredible graphics here. All right, so I've got some location here. This basically I'm going to do a series of drawings. I have some locations that emphasize on a sound wave. This is what I'm going to do, the overhead, just looking at the peaks. So at a moment later, some period later, that's where the sound wave is. So if you imagine a still pond, you throw a rock into it, that's the point. At some time later, the ripple's that big. At some time later after that, the ripple is that big. And sometime after that, the ripple is even bigger. So these are 4 moments in time. This object has not moved.